Hello, everybody. This is the 12th and last day of our NeurIPS marathon. Today, we're going to talk about the exciting field of mathematics and coding with AI. And we have a lot of slides to cover. We'll see. So there was a tutorial which was pretty extensive about generating programmatic solution, algorithms and applications of programmatic reinforcement learning and code generation. A very interesting approach, and I will explain why. So these are the authors here. It's a very big tutorial. We're not going to go through. It's about 2.5 hours. We're gonna touch a little bit upon the details. We're gonna mainly focus on the first part and a little bit on the last part. Learning to synthesize programs as interpretable. That's the key thing, and generalizable reinforcement learning, because that's where the problem is. The idea is that you have an environment, you observe the demonstrations, you have a reward function, you generate a program, you execute it, you continue this loop. As you know, typically in reinforcement learning, you have the environment, you make a move, you have an environment, you make a move, the move goes to the environment, you observe what happened or what's happening, and then you make another move or action. Okay, and the heart of reinforcement learning is obviously the environment, the simulator, but also this agent or policy network that decides what you're going to do next. And that's kind of like pretty neural. Okay, and of course, you also get the reward function inside the inside your policy network to make this decision. But the problem is that these deep neural networks, they offer, of course, they lack in interpretability, but they fail to generalize. Sometimes they overfit. I remember in one of my presentations a couple of years ago, when reinforcement learning used to be the hottest topic of NeurIPS. It was early on, before the language models became that big. They had this problem of overfitting, and let's say you had to train a reinforcement learning system. I should have put the slide here of learning to play Pong. And in order to avoid overfitting, they would put in the background a movie playing, okay, so that they would make sure that the system was picking up the motions of the Pong and don't get distracted by the movie. So they will add distractions, actually, so that it would learn to play Pong and not overfit. And again, here's the problem, that you get reinforcement learning agents that they learn how to work on a simple task, but then when you go to a bigger maze, they cannot do it. And the idea is to basically have a neural network that generates the policies as a program that you execute. The program can be a decision tree where you can actually add a verifier. It could be a symbolic program, if then else, or it can be a state machine. Okay, and of course, as I mentioned, there's this system called Viper, and one of the big things is that you can put verification mechanisms to make sure that your policy is conforms to standards. Let's say it has to do with flying an aeroplane, or don't say anything that you're not supposed to say. And these are kind of like some metrics: correctness, stability, and robustness. And the authors here have some statistics, some metrics. This is that idea of creating a state machine is quite old. It goes back to 2020. And again, you have to create the modes and the transition functions, everything that you need for when you so you're trying to create a transition function. That transition function will be your policy. Sometimes the environment can be a verifier if your goal is to basically synthesize a program. So in this particular way, in the general case, you want to create a policy that is solving a problem. But sometimes the output must be is not solving the problem. It's not, let's say, controlling a machine or a robot, but the output is a program. So the environment is the verifier. You just want to make sure that it's correct. And here's some systems like Doom is a system for playing Doom. Doom is a game which I think I was playing as a kid 30 years ago, when my computer had I think 4 megabytes of RAM, or 8. You needed 8 megabytes of RAM to run. That's to contrast about what we've seen in our lifespan.
And sometimes they call the computer opponent an AI.
Sorry?
Sometimes in those games you'd have a computer opponent, and in some games they refer that to the AI.
Oh, yes, that's true. So basically, here, in order to play Doom, you create, here you can see a simple program in Doom where this is what you generate, is that while front is clear, attack, move forward. If there is a demon, move right, else move left or move backward. So this is something that a reinforcement learning system can start, playing and losing the game and come up to a policy that it's a program and learn how to play. So you can actually take that and make it part of Doom. Now, the problem is, how do you generate the programs? Okay, and that's a whole, like, how do you go from a neural network to a program? Okay, and apparently we go back to the basic ideas of having a manifold of programs. So you need some kind, of an encoder that takes a program and makes it an embedding. And then you need, so that's a generative model, like you can think about a GAN for programs. And then from that latent space, you can generate programs. And this system called NeurIPS. So what happens is that you have to somehow this is your pre-training, okay? Before you go and you do your reinforcement learning, you have to somehow pre-train a model that knows how to generate programs. So after you do that, you use it to put it into your reinforcement learning pipeline. And in some cases, you have to put some hierarchy, because we know that programs are built in a hierarchical way to get better examples. And then people thought, okay, instead of creating a neural network, could I use a language model to do that task? Because that's already, a pre-trained, very capable neural network. It can also serve as your word model, as we saw previously, and maybe use that. In fact, I want to go back to the lecture with the talk that was about agents and playing games with language models, like playing chess. You can think about that as a reinforcement learning paradigm, where we use the language model for generating the next move and also being the world model. So that talk is very similar to that. So this system is called large language model guided search. So what happens is that you have a task-aware prompt. The map is an 8x8 grid surrounded by walls. I don't know, you describe the maze. Then you talk about some DSL that you're going to use. So you could use the whole Python, but you can describe your DSL here. And then you have the LLM. It generates a Python program. It's being parsed. I think that has to do more about making sure that it's correct syntactically. And then that current program goes into this neural manifold. So it's being embedded. And from that, you generate new programs. And then you interact with your environment. and you close the cycle. Okay, so the language model generates the seed. So, but you're still using this programmatic space to do your search. Now, you would also use the language model. You might avoid this neural manifold and do the regeneration. And there are some conclusions by doing that. It says the performance gains of LLM revision saturates with a few rounds. Combining large language model generated programs with search methods that can directly optimize returns is necessary. So I think these results are consistent with what we saw with chess. In chess, if you remember, you had an external controller, it was an external network that was generated candidate moves. And then there was the option of using the language model doing that. And the external controller was, easily achieving grandmaster level, but the language model was doing well, but it wasn't getting there. But of course, what people were doing is they were using, like, you can make your language model better by taking that neural manifold that you saw and generating more programs and fine-tune your language model and make it even better. I don't know if they tried it here, but that's the finding that they had from the chess game. So yeah, so the takeaways are that program synthesis times reinforcement learning is interpretable and generalizable. So we can see that as a great synergy or another path to the neuro symbolic dream vision. And of course, there are different world models. There's GenSim, there's Demo to Code, Eureka, language to reward. You can go and here they're working on physics, and I don't know. These are robots here. You can find more if you're interested. And there's a bunch of references, which unfortunately I haven't. Like, you will have to do the extraction of your own. There were too many to go with them here. I did my best. That was towards the end of my my journey, so I think I got tired. Another tutorial, actually, no, we're still in the same tutorial in the neural code generation. So we thought about, again, going back, what we've seen so far was reinforcement learning. Now we're taking the environment out. The environment becomes the verifier. So, this is purely for generating programs, not controlling anything external. So you can see AlphaCode 2, things are becoming better, models are becoming better. Of course, you can always improve by creating unit tests and adding verifiers. And this is kind of like a more complicated self-debugging via prompting with LLMs. We've seen a lot in text-to-SQL in several cases. You can argue that this is a long chain of thought, as we're going to see, because you're reflecting, you're putting several agents. This is an example. You have a C++, you say, well, create me an explanation. You're taking this, so this explanation can serve as a unit test. You can feed it back. You can ask for code explanation line by line. There's all sorts of tricks. I suggest, if you want to work on that, you watch the tutorial. But again, these are all tricks that you can use everywhere when you're using language models, okay, for solving tasks. So again, this is from an existing system. You can see the reference down here from ICML, and there is an example. Find the sum of the reciprocals of the root of this expression, and then you do self-reflection and all the stuff. You write programs, and then what happened is we're going back to the multi-agentic approach, where when you write code, you have the programmer, the test engineer, and they work together, they interact. You can have all sorts of agents, and in the end, you get a better program. So I think something that we have digested by watching the whole NeurIPS. Agents are here. You want to solve a difficult task. Don't expect it to be a one-shot decoding from a language model. And here the summary is pretty much we went through that, and open problems, long context understanding. How do you use retrieval augmented generation to it's another agent basically. Long-term reasoning and planning, code verification and safety. There's several talks in Math AI about that. We're gonna see. So if you want to read more, you can read that paper. It's quite extensive. Now we're gonna move to one of the papers from NeurIPS, which was an oral presentation. It's called "Divide and Conquer Meets Consensus: Unleashing the Power of Functions in Code Generation." So that's a little bit more manageable for people to understand. And I'll start with the motivation. LLMs only generate code tokens, non-stop, no debugging, no verification, no modifying, but the humans don't write code like that. The humans write short, maintainable code, decompose tasks into sub-functions, implement recursively. Functions can be reused. Sometimes we debug by looking into the outputs of different programs. Checking inconsistencies between programs help identify individual errors, and consensus often works. So this paper is trying to get all these principles and put them into a system. So it's called FunCoder, and it has this kind of like recursive approach. It takes a program, it puts stubs. Like you say, oh, I need a function that does this. Here, I need a function that does that. Then it tries to write these functions independently. It tests them, and it uses majority voting. We're going to see that further on. And so basically, if it starts building the tree. Okay, so it starts building a tree of things that will be generated now and things that are going to be generated in the future. And here's kind of like a full example where it starts. So it divides, and then it starts conquering and filling out all the stubs that it needs. Of course, there's always the problem that one of the functions can be wrong, so the whole program will be wrong. So it starts testing them, as I said, and several times. And if it sees that there is enough consensus, it realizes. So it will basically, so let's say for the function D over here, it might get 20 different functions by generating them again and again. And in order to pick the best, it will pick the one that gets the same results, agrees with most of the others, something like that. And, FunCoder seems to achieve state-of-the-art and better results. That's probably why it was picked as an oral. And again, this is the full diagram. MCTS is another paper, kind of like does the same thing. It's synthesizing multi-step programs using a verifier, an LLM, and tree search. More or less the same approach as we've seen before in the tutorial. In Daphne, that's the system, write a function repeat that takes an integer x and a natural number n as inputs and returns a list of length n in which every element is x. Then write a lemma repeat correct, that's x, that's for any x n. But anyway, so Daphne is kind of a verification system. And the whole idea is to basically recursively break the problem and also at the same time automatically write the tests, the verifications specs, which is quite a tedious work. You can read more on that. And you can use it Daphne or Daphne, Coq, Learn, Scala, or Rust. So there's more papers on coding. I just picked the ones that I thought they kind of like highlighted this where we are now. But now we're going to move to math. And for math, this was the workshop of the workshops, the Math AI, the fourth workshops on mathematical reasoning and AI. I spent a lot of time on that. I didn't attend it in person, but there's still a lot of papers that have very charming titles, and I haven't been able to go through them, but I put a list for you. That was definitely a long keynote from Don Song. And I think if you want to get an idea of where we are, like a review, you should definitely watch that. Formal Mathematical Reasoning, a New Frontier in AI. And, you know, there's definitely a lot of, they're on the spotlight from the big companies, OpenAI, you know, DeepSeek, DeepMind, and there's big prizes, $10 million. Companies like XTX Markets, and then we have the Artificial Intelligence Mathematics Olympiad. And here you can see how different systems perform. You know, why AI for math? I don't think we need a lot of motivation. Math is a hallmark of human intelligence and the foundation of, you know, complex reasoning, STEM, probably safe and secure systems. And as I've mentioned before, we've seen during this journey that if your LLM is good at math, is also good at other things. And that's kind of like the informal approach. You know, this is how Numina Math won the first AI Mathematical Olympiad Progress Prize. They start with a pre-trained model, Vanilla 1. They put math-related web documents, continue pre-training, they get a model. Then they fine-tune it with problems with step-by-step solutions. They get something better, and then they also fine-tune it with problems that they're actually using tools. So you see the solution here says, let's use the SymPy to evaluate that. So this could be something that's a recipe you can use in other problems. And the question, as you can see, is how do you get these data sets? You know, that part I think we all know with the language models. But how do we go from this big, you know, more generic to more specialized instructions is the problem. And of course, you know, we just said that the limitation is the data scarcity, and of course the lack of verifiability, which I think this one we're becoming better. Actually, in both we're becoming better. So people move to formal mathematical reasoning because usually the most of the problems we have, they're coming from textbooks, which they're all expressed in natural language with some symbols, but we would need the formal language. So mathematics, of course, logic is the language of mathematics. We know that. And we kind of like need to have a computer programs and formal specifications. So you need to be able to run these proofs in a formal language. And GamePad was one of the first kind of like, you see Ilya Sutskever here. I don't know how old this is. Yes, it's 2019. It was the first approach. There's kind of like a DSL here. I think this is Koch. And of course, right now we have, you know, we have Isabel Koch and Lean. They're all quite popular. There's pros and cons, but I think Lean is becoming the theorem proof of choice. And by the way, you can do other stuff with Lean. You don't only have to do math. You can also do I don't know, any formula. Like you can do, people have tried to do law with that. And this is how you go from the proof tree to Lean. And there's like the MathLib 4, which is a big library. People are trying to move into Lean thousands of known theorems. There's a big project. And this is kind of sad. I got this email a few days ago. You know, basically this says we're working on an open source project initiative. And they're looking for individuals that they are skilled in Lean form and MathLib. They also know advanced in mathematics. and they basically need to solve some problems that they are, I think it's the mathematical Olympiad. Okay, and it would be fantastic if you do that, but they're going to pay you $30 to $40 an hour. That was scary. And you get $34 an hour, you fine-tune a model or you contribute to a model. I don't know. Then one of the big ones get the data sets, make a better coder, you lose your job. I don't know. And I tried. There's a form. Apparently, I don't think it was good enough because I haven't done Lean for a long time and I couldn't remember it. But that's kind of scary. I mean, it's interesting, but also scary. It raises a question to me. I'm going back to data monetization. This is wrong, $30 or $40 per hour. I will contribute that, but we need to have dividends on that. By the way, since we're talking about, there's a whole community called Radical Exchange that they're working on that problem. And that has implications in economics about universal income and data monetization, and like, how are the white collar employees look like in the age of AI? Okay, so yeah, that flat model I think is going to go away. We will need to get royalties out of the data we sell to language models. So here's an example, larger scale system, the alpha proof. They had some informal problems. They use this thing, we're going to talk about this, the formalizer. So informal problems means things you get from a textbook in natural language. You convert them into a language like Lean. So you go from 1 million informal problems to 100 million, because you also do some synthetic generation. And you use this kind of like, I think it's reinforcement learning, you can call it. It's a solver network. You get formal proofs, you train it. Yeah, you can. It's a loop. I don't think if it exactly fits the definition of reinforcement learning, but it doesn't really matter. You have a model, you fine tune it, you generate more formal proofs, you retrain it, and they got a silver medal. But recently, they actually got the gold medal with alpha geometry 2. And it's actually even scary because I think, so here's the thing. Before, they didn't do well because they defined it the DSL. So you can see it's a DSL that kind of like describes geometric problems. And that could cover only 66 of the problems that they would see. And then they expanded their notation, so now they can cover 88%. I don't think they can cover problems in 3D, or they're still like. There's obviously going to be another version that is going to be able to express other problems. But I think out of these 88 problems, they got 86% correct. If I remember, I read the paper, which is scary. I think 84% of all geometry problems, 84, and they're able to cover 88. So this is pretty, like if you normalize it, it's high 90s what they achieved. And I just put this book here, which was recommended from my good friend Moham Aref, where he kept saying that notation matters. So, and we have programming language people here in our audience. And that kind of like tells you that we're going to see that again. The way that you represent problems with the language models, your notation can have a significant impact. We've actually seen that through these 12 days of NeurIPS a lot. How you present the problem matters a lot, and we're going to see it today later. So let's go back to the problem of how to overcome the scarcity of formal data. So there is, again, this loop. There's this project, I think that was last year. We have it on our last year presentation of NeurIPS, the lemma, or code that I think that was used to train the code llama. And basically, they use this loop where you take informal proofs, you auto-formalize them with a language model, you train it, you correct it, and you generate more. Yeah, so here's the loop over here. Informal auto-formalization, formal math statements, model scoring, and hypothesis. So you kind of have some weak supervision. Okay, that's kind of like the idea. In some cases weak, some cases strong. Strong is the theorem prover can tell you if your proof is correct. but there are some weak verifiers involved too. So alpha geometry, as we saw before, managed to get 100 million synthetic data. You can find the paper, more details on the paper. And of course, that's like an exciting field where you want to automatically create more and more theorems. So you have this conjecturing, and so it's an art of how you automatically generate conjectures, and then you pass them through a theorem prover to see if they are correct, and then you use you basically generate a theorem, and then you have the checker, lean or something else to tell you if it's right or wrong. So yes, so you can read more on that paper. That's another paper about autoformalization. Again, we went through that. We saw that before, hierarchies. We saw that in code generation, hierarchies are also important for theorem proving. So exploiting hierarchies, it's also interesting. Another paper in that spirit, informal problems, formal solutions, generate multiple informal solutions and auto-formalize them. So that's kind of like another way. So you can do basically your conjecturing on the informal space, not in the formal space. Something else that it's interesting, I think, and we should look at that. The mathematicians, they built a tool because, when you're trying, there are right now efforts to translate proofs of theorems that are like 200 pages, like the Fermat theorem. And this is a very famous one, the polynomial Feynman-Russa conjecture, that required this insane system, like contributions from all over the world working together in order to formalize this proof. And as I said, formalizing the Fermat theorem, it's an enormous task, but it's something that we have to do because if you don't know, when Andrew Wiles, I think was his name, sent the proof, there were probably 2 or 3 people in the world who could read that proof, and they needed a year to verify it. Okay, so for a year, these people that they were paid mathematicians, they had to do their own research, they had to drop everything, and work for a year to say, okay, and actually after they worked for a year, they realized there was a mistake, and then he had to go back, work on it, and then spend, I don't know how many months to claim that. So I think in the future, these proofs will have to be written in a formal language, and we will have to need theorem provers, like Lean to verify that they're correct. And this is a quote from the Free Think GitHub CEO says, Copilot will write 80% of the code sooner than later. And next 5 years, bring community together to advance AI for formal math and theorem proving. Anyway, so that these were some kind of results or conclusions from this humongous keynote. And I should have put that also in the agents. This is an interesting course that Berkeley is giving. So it's called llmagents-learning.org. That's the website. They already gave a course on LLM agents with 14,000 people enrolled. You can find the material. Wish I had the time to go through that. And then they had a hackathon. And now in spring 2025, it says Advanced LLM Agents, AI for Theorem Proving. So if you have the time, just register. I think it's free. Now, I want to go back to simpler mathematics, which is arithmetic, and kind of this could have been also in a different session, but this wasn't at NeurIPS. This is very recent. I think it has been submitted for ICLR or ICML. I don't remember. There's a video you can watch. And this has been, let's say, oh, mathematics are trying to prove language models are trying to prove mathematics. This is great, but you know what? LLMs cannot do addition, and people have have been challenged with that for a long time. And in general, like they might be able to solve addition for, you train it for up to 10 digits, and then, it generalizes up to 20, and then it starts dropping. And that generalization to arbitrary length has been a big challenge for language models. And people know that, they know where the problem is. It's the representation of numbers, and they go and they, if you change the tokenization and you change the transformer, you can actually solve the problem. We know how to solve it. The problem is that we don't want to go to a specialized architecture for that. And people have posed the question, is it possible to solve at least the addition problem? And as we're going to see even more, by staying on the traditional architecture and next token prediction. And one problem which is particularly interesting for us here at Relational AI is finding paths and shortest paths, because you can always teach a language model to find shortest paths on a graph. It will generalize on that graph, but it won't generalize on a new graph. And one of the problems you have to think about is that when you do addition, you do it in, you first do the least significant bit, but when the language model is writing it, it's writing the most significant bit. That it means that it has to do things ahead of its time in memory. Okay, so it would be great if you try to do the addition and do it first in the reverse order, 5, 9, 4, and then reverse it, you already do better. So this is the plane. This is if you do it in reverse. So if your chain of thought is, okay, I'm doing it in reverse, and then I'm going to reverse it. Okay. And then it's the simplified scratch pad, where you're basically giving it the algorithm, how you do it. You show digit by digit. So it's a kind of like a small chain of thought. And then if you use the full algorithm, where you describe what you carry and blah, 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 then you do even better. So again, data format has dramatic impact on the underlying function to be learned. Okay, so this is a simple function, and by doing these tricks, you can learn it better. Remember when we talked about mathematical Olympiad, where you are trying to learn even more complicated reasoning functions over there and patterns, your notation mattered. Okay, and we can do better because LLMs can actually self-learn. And they actually noticed something that, let's take this. In round one, they train a language model to learn. Okay, so in round one, they train a language model with 10-digit data, how to do addition with this reverse addition thing. And you see that it learns how to do that, but once you go to 12, it starts degrading. Okay. So what they basically do is and then the same thing happens here. So you teach it with 12, and then it goes maybe up to a state, and then it drops again. So what they're doing is basically they're doing such training. So you train it for 10, which means that you can train safely for 20. And what they do is that they basically have a verifier, but not a verifier that actually goes and do symbolic addition. It's a weak verifier that knows how to select training data, because as you can see, even at you train it at 10, even at 12, you still produce something, which is good. So you can do for sure 11. At 11 you are 90%. And so the main idea is, in fact, you can go, if you can see, I don't think that was the final label, but yes. So I think, I'll take it because I don't remember. It's in the presentations. If you train it for 10, it successfully generalizes to 20 addition. So you take that as a way of generating data up to 20, and you use a verifier to make sure that they're good. And then you go and you retrain your model, and now we can go to 30, and you retrain, and you can see that with this tactic, they went all the way to 100 digits. Okay, and there's also some papers over here, like Pattern Booster does this for paths. Okay, so the idea is you train a model, and that model bootstrap itself, and you can do the same thing for solving mazes. So you start with a small maze, you generate data for a slightly bigger, you verify it, and then you make it bigger and bigger. And that's kind of like a strategy about how you are fine-tuning indirects, because you keep adding more and more data. So what happens is you took the data that they were learning how to do 10, you split them in half, and now you get it for the next round, and you keep doing that. So you always keep your training data constant. And they believe that it's a better way to sample for harder problems. Anyway, and here's like more references. Okay. We're actually not going to go through this presentation because we covered that at a previous session on the scaling laws. It is a great presentation. It was one of my favorite. It was from OpenAI. Surprisingly, although it doesn't have to do with math, but it has to do with reasoning. It's about how to scale LLMs with games. So I'll just fast forward here. Okay, and I go to the next subject, which is finding interesting mathematical objects with language model, and this has to do with automatic conjecturing, and that's a paper from DeepMind. And sometimes it's more helpful to disprove theorems. So, people create conjectures, and they can say, they can find when it's valid. And basically, I'll just go quickly over here. Proofs are important in mathematics, but for many problems, this is not the focus. Finding good construction is often a crucial bit. Counterexamples to conjectures. Knowing the optimal constructions for large parameters lets us spot patterns. That's another way of doing it. Lead to explorations, new conjectures, new theorems. And here's from Gil Kalai. The methods for coming up with useful examples in mathematics are even less clear than the methods for proving mathematical statements. Okay, I think if you ever been in theoretical mathematics, you've seen that a lot. I'm interested in simply useful ML tools that we can give mathematicians to use to search for such objects. So the author goes a lot of examples and a lot of conjectures. I think it's a little bit beyond the scope of this presentation because they're quite theoretical, but they're very interesting if you're in the graph space. And I like this one. It says sometimes theorems can be cast as questions. So that we're becoming interesting. How many points can we choose in the n by n grid without choosing 3 points that satisfy distance of a comma b equals to distance b comma c without creating any isosceles triangles? That could have been a data log query. That could have been a SQL query. So that's why it's interesting to look at these papers and talks over here, because if you want to solve enterprise problems like text to SQL, you might actually be inspired by the methods they're using here. And then it goes on about the isosceles triangle problem and what they're doing. So there's some interesting question. And of course, there is this question over here. It says, there's a conjecture here. The vertex edge of any polytope with n facets in d dimension, dimension d, has diameter at most n minus d. And this problem is like, how hard is linear programming? That goes, so the author moves from graph problems to polytope problems, and linear programming is actually associated with the hardness of polytope problems. So you can see some fantastic papers. I put the references later on. Actually, I couldn't find this one, the advancing geometry with AI, multi-agent generation of polytopes, but this looks like a fascinating area. And we do have someone here at Relational AI, Randy Davila, who has addressed the same problem without language models. The paper is called "The Optimist Towards Fully Automated Graph Theory Research," and it does look like an agentic model, but he's using symbolic methods and integer optimization to automatically create conjectures. We have questions from the audience. Surprisingly, I think I have a hunch that this can because it's actually interesting. It's based on two agents: the optimist agent and the pessimist agent. So I think it screams for taking this technique and combining it with a language model, which is my next project. Of course, that wasn't part of the Math AI workshop, but as I said before in this presentation, anything that we see relevant that has been published recently, we don't miss the opportunity we don't lose the opportunity to put it there. So AI for mathematicians, this is more about how AI can help mathematicians. I mean, obviously, what we talked before, automatic conjecturing, was in the same spirit. That's another talk. There's two traditions in AI: symbolic AI and formal methods, machine learning and neural networks. The strengths are complementary. Symbolic AI is good at getting details right, but gets lost. Machine learning is good at synthesizing data, but we don't know what the results mean. Both are important for mathematics. And AI for mathematics is not about getting the right answer. It's about providing tools that helps us reason mathematically. AI for mathematics is AI for mathematicians, actually. I like this human approach. And whether you like it or not, we are all mathematicians. And then it talks about the mini CTX, kind of like a productivity tool for mathematicians. Improver, it's an agent-based automated proof optimization. Again, they're all in the same spirit. Let's see which systems are going to prevail, but they're definitely worth investigating. And we need this. Maybe this is where I'm going to be my next workshop proposal for NeurIPS is, and reach out to me if you want to be part of that proposal, is how we can transfer all the things we learn from math and AI to enterprise problems. Okay, the enterprise has a lot of reasoning problems. So this agent-based automated proof optimization system, Improver, which is based on three metrics: layered declarativity and the mixture of two, and has applications, user end tools, data augmentation, optimizing data for training. I mean, this could be a tool for a data scientist in the enterprise. So let's see how we can make the jump. I like that author. He had some philosophical statements here. It says, getting priority straight, a common distinction, basic science, understanding the basic principles with which we can train a system to exhibit intelligent behavior. But there's also the engineering, meeting the design challenges that are needed to deploy such systems and make them useful. And he wants to push back against this way of looking at things. I have to say, I just remember that, I was just trying to finish the content of Math AI workshop. And I said, I think I'm done with the talks. And then I will see the slide of the next talk and I say, oh, that also looks interesting. And that was one of the talks that kind of like got me going. And again, the author is continuing his claims over here. And he has it in this kind of like dialogue way. I'm just going to read that because I find it entertaining. Getting AI to do mathematics well requires a combination between machine learning and formal methods. Okay, we knew that. I may be wrong. This is an empirical question. Getting AI to do mathematics well includes having it generate formally checkable proofs. Why not? I am a mathematician and I want formally checkable proofs. Getting AI to do mathematics well means making it useful for mathematicians. This is what we mean by doing mathematics well, and we're all mathematicians. And this is the closing motto: AI for mathematician equals AI. AI for mathematics equals AI for mathematician equals AI for everyone. And again, maybe the next paper is in that spirit because it's coming from JP Morgan Chase AI Research. and it talks about learning mathematical rules with large language models. And again, these mathematical rules that they go through, here I'm just sweeping through the slides. These are mostly mathematical formulas, but they can be mathematical formulas to for business. So this automatic conjecturing, automatic rule construction has a great application to business. And the takeaways from this talk is fine-tuning models on some specific mathematical rules allows them to be reused in the context of word problems, bottom-up generalization, and training on multiple tokens improve the model's ability to generalize specific rules such as distributivity and manipulating equations. This is a top-down generalization. But again, it's really strictly to algebraic formulas. We want this to more realistic. And here are the references. And here's even more references. Open Math Instruct, you can look at the talk we had yesterday about dealing with data. I'm just going to mention very quickly. This is about generating 1.8 million math instruction tuning data set by using Mistral and not using anywhere in distillation any commercial model, because remember, one of the problems that's good for data scientists to know, if you're using a commercial model for distilling information to train a smaller model, you're already bound to the licensing agreement, which means that you cannot compete with Gemini or OpenAI or Claude, whatever you're using. So this paper talks about, again, it's for mathematics, but you can apply it in other places, about how to distill, how to take a smaller data set and create more synthetic examples by using, let's say, Mistral, who has a much permissive license. This is my 20 papers from Math AI that I haven't been able to read yet, and I hope some of you can read. Did I say 20? There's another 14. There's for 34. And we are basically done. Here is the book of trends in AI 2025 based on NeurIPS. And I want to thank you all for, I want to thank Relational AI for giving me the time to do that. That was hundreds of hours of work. And I also want to thank everyone who attended, and I hope you found it useful.